Hello everyone, this is Dr. K. Purani, Assistant Professor of Mathematics, Arimugu Palani Underwood Arts College for Women, Palani. In this lecture, we are going to discuss about connectedness theorems in topology. Before we are going to theorem, first in the previous lecture itself, I explained what is separation and connected. Just to recall that this is a separate definition. If these four conditions are satisfied, then this is separation. U V non-empty and their intersection is empty. Their union equals whole set, and U and V are open. If a space X is said to be connected, then that does not exist separation. That means separation does not exist. If separation exists means then that the space is not connected. Okay. Now let's see the theorem. What's the theorem? If Y is a subspace. If Y is a subspace of X, A and B form a separation of Y. If Y is a subspace of X, if A and B are form a separation of Y. If and only if A and B are disjoint, non-empty, whose union is Y, and neither of which contains a limit point of the other. Neither of which contains a limit point of the other. That is A dash intersection. That is A dash intersection B equal to 0 and A intersection A intersection B dash equal to 0. Okay, this is the characterization theorem. So we want to prove both parts. First we prove first part. What is the first part? What is the hypothesis? Okay, wait. What is the hypothesis? What is the hypothesis? A and B form a separation. A and B form a separation. Then A and B form a separation means by the definition A, B non-empty, their intersection is empty. Their intersection is empty. Their union equals Y because A and B form a separation of Y only. Then A and B are open in Y. Okay. What we want to prove? We want to prove that A dash intersection B equal to 0 and A intersection B dash equal to 0. What is A dash and B dash? It is nothing but A dash equal to derived set of A, that is the set of all limit points of A. B dash equal to derived set of B, that is the set of all limit points of B. Before we want to prove that, first we all know that what is limit point. Okay, we want to know what is the limit point. Come to see what is the limit point. Okay. See, let x comma d be a metric space. Let A is a subset of X. Let X be a point of capital X. Then the point X is called a limit point. Limit point of capital A. If every open ball with center X contains at least one point of A different from X. What is the difference? What is the definition? Every open ball with center X contains at least one point of A different from X. See the figure, you can easily understand. See, every open, this is the metric space X. Let X be a metric space, then A is a subset of X. So, this is the subset A. See, this is the open ball. Okay, a open ball with center point. That is X சென்டரா வச்சு வரையக்கூடிய ஒரு ஓப்பன் பால்ல அந்த ஓப்பன் பால்குள்ள இன்ஃபினைட் நம்பர் ஆஃப் பாயிண்ட்ஸ் இருக்கும். அந்த ஓப்பன் பால்ல எக்ஸ் சென்டர் பாயிண்ட் எக்ஸ் அல்லாம ஏதாவது அட்லீஸ்ட் ஒரு பாயிண்ட் ஆகுது இந்த சப்செட்குள்ள இருந்தா அந்த பாயிண்ட் எக்ஸ் அப்படிங்கிற அந்த பாயிண்ட் வந்து நம்ம என்ன சொல்லிடலாம், லிமிட் பாயிண்ட்னு சொல்லிடலாம். ஸோ இன் திஸ் ஃபிகர் ஏ ஆல் த பாயிண்ட்ஸ் ஆர் contained in the subset A. So come to the figure B. Here is X is a metric space. This is the subset A. See, in this open ball, this is the open ball. There are infinite number of points in this open ball. It is the center. Okay, subsetக்கு வெளியில open ball வரைஞ்சிருக்கோம். Center point Xங்கிற center point Aங்கிற subset குள்ள இல்ல. What is the definition? In this open ball with center X center வச்சு வரையக்கூடிய open ball at least one point of A different from X. ஏதாவது இந்த ஓப்பன் பால்குள்ள இருக்கிற ஏதாவது அட்லீஸ்ட் ஒரு பாயிண்ட் இந்த சப்செட் குள்ள இருந்தா போதும். See here, this point is contained in, yes, this point is contained in A. So you can easily understand that. Okay, now come to the figure C. See, this is the metric space, this is the subset. See here, the open ball is totally outside the subset. Okay, in the open ball, fully in the metric space, but not contained in subset A. See, in this x சென்டரா வச்சு வரையக்கூடிய ஏதாவது ஒரு பாயிண்ட் ஏக்குள்ள இருக்கணும். See, இதில் ஒரு பாயிண்ட் கூட ஏங்கிற சப்செட்குள்ள கண்டெயின் ஆகி இல்லை. ஸோ ஃபைனலி we can what we can say, finally we can say that figure A and B, okay, figure A and B are limit points of A. See here, one point is contained in A, total all the points are contained in A, but here no one points are contained in A. So figure C is not, this is the example. Okay, figure C is not a limit point of A, and figure A and figure B is a limit point of A. Okay, இப்படி ஒவ்வொரு open ball, you know, in this metric space there are infinite number of open balls. Okay, infinite number of open balls. ஒவ்வொரு ஓப்பன் பால்லையும் ஒரு சென்டர் பாயிண்ட் இருக்கும். ஓகே, அந்த சென்டர் பாயிண்ட்டை வச்சு வரையக்கூடிய இன்ஃபினைட் நம்பர் ஓப்பன் பால்ஸில் அட்லீஸ்ட் ஒவ்வொரு ஓப்பன் பால்லையும் ஏதோ ஒரு பாயிண்ட் இந்த சப்செட்குள்ளே இருக்கணும். இருந்துச்சுன்னா we can say that it is a derived set. Okay, the set of all limit points of A is called a derived set. It is denoted by D of A or A dash. Okay, this is the definition of limit points. Now come to the theorem proof. Now see, we want to prove that A dash intersection B equal to empty, A intersection B dash. Just we see what is the A dash. Okay, since A union B equal to Y and A intersection B equal to empty, okay, A intersection B equal to empty, we can say A is open, so A complement, that is A equal to B complement. A is open, then B complement, Y minus B or B complement is closed. Okay, now take B is open in Y. Okay, now take B is open in Y, then B complement is closed in Y. This implies what is the B complement? A. So A is closed in Y. If A, in all of you know that if A is closed, then A equals A closure. If A equal A closure, then A is closed. So we use this result here. Okay, we use this result. Closure of A equal to A. A is a subset of Y is a subspace. A is a subset of Y. So A intersection Y equal to, we can get again A. A equals A closure. Okay, so we can write instead of A as A closure intersection Y equal to A. Okay, here then in the next step intersect B. Okay, intersect B on both sides, we get this. Okay, now A closure intersection Y intersection B equal to empty, because A intersection B equal to empty by the hypothesis. Okay, so empty. Here A closure intersection B, because B intersection Y equal to A intersection Y equal to A, B is a subset of Y means B intersection Y equal to B. B intersection Y equal to B. So A closure intersection B equal to empty. Okay, we use here the distributive law. Okay, we use the formula A, we know the result, closure of A equal to A union A dash. So instead of A closure, we can write A union A dash. Okay, in the next step only, we use distributive law. See, we use the distributive law. Okay, see, A intersection B equal to empty, and okay, this is okay. Now the final answer is A dash intersection B equal to empty. So we proved one result. Similarly, we can prove that B equal to A complement, and A is open in Y means B complement is open. B complement is closed in Y. That is A complement is closed in Y. That is B. So B is closed in Y. We get the final answer A intersection B dash equal to empty. Therefore, we can prove one first part. A and B, if A and B form a separation of Y, then we get A dash intersection B equal to empty and A intersection B dash equal to empty. Now we prove the second part. What is the second part? Conversely, assume that A and B are disjoint non-empty sets whose union is Y, and neither, which that is A dash intersection B equal to empty and A intersection B dash equal to empty. Okay, see here, this is the hypothesis part. Okay, sorry, this is the hypothesis part. This is the hypothesis. We want to prove what? A and B form a separation. Just we want to prove A and B form a separation. A and B form a separation. Okay. That means what? A and B form a separation means we want to prove just four conditions. What is the condition? A, B, non-empty. See, in this hypothesis, three points are satisfied. What is the point? A and B non-empty, A intersection B non equal to empty, their union equals Y. So it is enough to prove that the fourth condition. What is the fourth condition? A and B are open. So it is enough to prove that A and B are open in Y. Okay, we have by the hypothesis A intersection B equal to empty, A dash intersection B equal to empty. So we union these two, we get equal to their union is also empty. In this next step, we use the distributive law. Sorry, yes, we use the distributive law. A union A dash intersection B equal to empty. We all know that closure of A equal to A union A dash. So instead of A union A dash, we can write A closure intersection B equal to empty. Here intersect union A on both sides. Okay, we get this. Okay, next also we can use the distributive law. We get finally we get A closure intersection Y equal to A, because A is always subset of their closure A closure, and A union B equal to, this is the hypothesis part. So we can write A closure intersection Y equal to A. Okay. We can write A intersection Y equal to A. Okay. Then if A intersection Y equal to A means closure of A equal to A. Closure of A equal to A. If closure of A equal to A means it is a if and only if proof A is closed in Y. Okay. Similarly we can write similarly we can prove B is closed in Y. Since A equal to B complement. Okay. See here. Um, we have B is closed in Y. Since B is closed in Y, B complement is open. That is equal to A. So A is open. Since A is closed in Y, we get A complement is open. That is equal to B. So B is open in Y. Therefore, A and B are open in Y. Okay, we proved that the fourth condition. So it satisfies four conditions. So we can say that A and B form a separation of Y. We can say that A and B form a separation of Y. So we proved the second part also. Therefore, hence the proof.